Okay, so question 50, given the following free energy diagram, answer the following questions. So this is my approximation of the free energy diagram in your book. And so I'm going to answer the first four questions. The last four questions are a tad bit more challenging, and so you need to try to tackle these on your own. So the first question, how many intermediates are formed? So the first thing you need to be able to do is put down the definition of an intermediate and how is it different from transition state. So intermediates are going to be the product of one step of a reaction, and they're going to be a reactant in the next step. So basically what this is telling you is that when you see this kind of diagram, the starting material or the product are immediately discounted as being an intermediate. So this is the starting material right here. I'll just abbreviate it as SM, and this is the product. I'll just abbreviate it as P. So compound A and compound D are immediately taken out of the mix as potential intermediates. Okay, a second criteria for intermediates, or an aspect of intermediates that you'll see a lot of the times, is that the intermediates are going to have relatively high energy when you compare them to the starting material and the product. So you'll want to look for something that's higher in energy than A or D, and then from there we basically have to decide between whether we want to have these local maxima as an intermediate or local minima as an intermediate. So from here, basically, the way you determine the difference between intermediates and transition states is that all of the intermediates or potential intermediates are going to be local minima. Okay, so what that means is that as this line curves down and as it curves back up, this is going to be your local minima. Okay, so this compound B is going to be one intermediate, and this other local minima at compound C is going to be your other intermediate. So both of these guys are going to be intermediates. Okay, the difference between the intermediates and the transition states is that the intermediates are potentially isolatable. So they have formal, formally covalent bonds. So you can actually, if you had the most powerful microscope in the world, and let's say you could potentially ever see these guys, which you could never actually do with your naked eye, if you looked at them, you would see that if B had a bond between atom A and atom C and atom X, that bond would be completely formed. Okay. The difference between the intermediates and the transition states is that transition states are super high energy. They're really, really high energy. They're really, really unstable. And a characteristic is that these transition states, or the local maxima, are going to have incompletely formed and incompletely broken bonds. So let's say we have, I don't know, atom X and atom Y. Normally, you could potentially have a bond between these two, but what this local maxima is telling you is that there may or may not be a bond in between X and Y, but it's either being formed or it's being broken. And it's in the process of being formed and being broken. And this partially formed or partially broken bond is going to be extremely high energy. Okay, so these guys are notated with generally these brackets, and you see this double dagger and superscript to the right. So this double dagger with this bracket is going to immediately, or it should immediately, indicate to you that this is a transition state. It's extremely high energy. It's unisolatable. You cannot isolate it. Okay, and so also an easy way to think about it is that they're local maxima. So this is a local maxima, so is this. This is a local maxima, and so is this. This is a local maxima as well. Okay, so each one of these, here, here, and here, are going to be transition states. So the answer to question B is going to be 3 transition states are going to be formed in this reaction going from A to D. Also, to answer the first question, how many intermediates, we're going to have 2 intermediates, and these are going to be compounds B and C. Okay. So then let's think about sub-question C, which is the fastest step in the reaction. So we're going to be able to, this is a very easy call to make, and basically what this is dependent upon is this term, this delta G double dagger. And what this is indicating to you is how much energy is needed to get from a reactant to the transition state. So basically what this is saying is, let's say we go with our starting material A, and we draw a baseline. Let's just draw a baseline going like this. So the difference in free energy, which is, I neglected to label this graph, on the y-axis is our free energy, and on the x-axis is our reaction progress. Okay, so this is a very good example of why it's important to always label your axes. But anyway, on the y-axis is the free energy, and if we draw this baseline here, the difference in the free energy from this flat part to this local maxima will be this quantitative amount. Okay, and so the fastest step in the reaction is going to be the step that has the lowest delta G double dagger. So we're going to have overall 3 delta G double daggers. So we're going to have that first double G double dagger. We're going to have this double G, or delta G double dagger. And we're also going to have this delta G double dagger right here. Okay, so the fastest step is going to be the step that has the smallest delta G double dagger, and it looks intuitive at this point now that we've drawn these kind of horizontal lines from starting material to transition state to product or intermediate, that this step going from C to D is going to be the fastest step in the reaction, where we have a really, really small delta G double dagger. Okay, so the fastest step is going to be going from C to D. Okay, so that's going to be the fastest step. Okay, so which is more stable, A or D? So again, overall, in terms of stability, lower energy equals lower or higher stability. So the compound that's going to have the lowest G, or free energy, is going to be the compound that's the most stable. So obviously, C is right out because it's one of the highest intermediates. C or B is also one of the highest intermediates. So comparing B and C to A is a little bit more stable than B, as well as a little bit more stable than C, but it's still less stable than the final product, D. So if we think about the energy difference between A and D, so we can just walk along this horizontal right here, we're going to have a total energy difference, or free energy difference, between A and D that equates to this much energy. So overall, D is going to be lower in energy than A, and so it's going to be more stable, so D. Okay, so you got 4 more sub-questions for this overall question. Try to take a stab at them, and if you have questions, feel free to chat with me about them. Okay, next question.